Hello everyone, my name is Juan Pablo Valdes and I'm a PhD student at Imperial College London. And today I'll be presenting our proposal on how mixing processes could be designed from physics-informed algorithms. Nowadays, nearly every product that we use on a regular basis has undergone some sort of mixing during its manufacturing. And this process has been crucial in determining both the quality of the product as well as the efficiency of its production. However, mixing remains a largely inefficient and poorly understood operation, being heavily dependent on empirical methods and design heuristics. And this has commonly led to overconsumption of both energy and materials, as well as production yield losses and costly complications in the process scale-up. And the root of all these problems really stems from the lack of fundamental knowledge on the mixing itself, which cripples the design methodologies that are available to the industries. For this reason, we would like to explore an alternative based on the new wave of data-centric engineering practices, where we propose a design stage that is directly connected to a robust physics-informed model of the real-life system, commonly called a digital twin. And this model is comprised of two sections. One, a high-fidelity, massively parallelized CFD code, and a machine learning algorithm. And the novelty of our approach here really lies on the revolutionary interface tracking algorithm that is embedded in this CFD code, which grants us with a wealth of information on the underlying physical phenomena occurring in the mixer, which is completely inaccessible through experiments or other modeling approaches. In this way, we're able to provide robust and efficient solutions based on the physical phenomena rather than by trial and error iterations or heuristics. Our code can provide valuable insights of numerous industrially relevant scenarios. For example, we have been able to elucidate how different flow field parameters relate to the complex dispersion dynamics that take place in static mixers. Or we have also been able to study highly turbulent mixing systems where we can capture the impact of complex vortical structures, or also study the altered dynamics behind droplet breakage in the presence of certain contaminants. And regardless of the radically different physical conditions of all these scenarios, we're always able to identify and isolate recurrent mechanisms that could help further on in the design process. And all these fundamental analysis can be translated into practical information, which can be directly used as performance indicators of the mixer itself. So with this new framework that we're proposing, we could definitely shift the current design paradigm, transitioning from empirical-based heuristics to rigorous physics-informed decision-making. And in this way, we are able to explore in a flexible way unconventional and potentially counterintuitive designs without incurring into further costs or causing negative environmental impact that usually comes as a result of unnecessary experimental tests or pilot plans. Thank you very much for listening.